What is up, guys? How's it going? So, today we're going to be talking about parsing a variable declaration. And this is pretty much going to be the last thing that we're going to talk about before we start getting into parsing expressions. So, we're going to kind of talk about how to parse a variable declaration, and then I'm going to do an overall general recap on pretty much everything we've gone over, just to make sure that you guys properly set up your parser and to make sure you have the appropriate function calls and checks in place. So let's just kind of go over, like I said, variable declarations first, and then we can do that afterwards. So the first thing you're going to want to do is, of course, have it is check. And for variable declarations, it's a little bit different in how I try to figure out, what qualifies as a variable declaration. So in my language, if you guys know, like typically you create a variable declaration by having the name, having either a colon or the infer symbol, then you have your value or you have your type depending on the formatting that you chose to set up your variable declaration. So we're going to have to check that to validate that it's in fact correct. So all you're going to want to do for your is check is you just want to check to see if the current token isn't a keyword and it's an identifier. Once you do that, then we can basically do our additional checks. So we need to see if the next token after our current token, so if our current token is basically an identifier and it's not a keyword, then we want to check our next token to see if it equals a colon or the infer symbol. Or if we have a storage type, basically a storage type is thread local, and this is check basically allows us to have support for thread local variables. So thread locals in my language isn't really considered an access type or an access declaration. They're treated a little bit differently. We'll go over thread locals and how they work on the back end side in a little bit, but yeah, just make sure you create this itch storage type and you check to see if the current token is a thread local. So otherwise, if we have our current token and it's not this case, well, then we want to check to see if we have a storage type and then we have a variable declaration after that. So you want to check one or the other, right? So you want to check, is it this formatting where you have your string, your colon, or your infer, or is it this format where it has a storage type, your name of the variable, and the appropriate colon or infer symbol. So it's going to be either one of these or, let's see, I'm going to say thread local, some variable of type int. So this would basically be the third formatting. So you have this formatting, and then the final formatting. So let's kind of see how this looks practically in the code. So basically, once we determine that this is true, then we want to parse a variable declaration. And in there, we want to create a AST variable declaration branch. Once we do that, we are going to support multiple variable declarations. So in my programming language, the way that I'm going to do it is, so like you have the name of your variable, and then you have like the type, or you have the colon denoting that you need to specify the type of the variable. And then you can also have A, B, I'm going to come up with some very terrible names here, as usual. But you can also add multiple variables that basically share the same type as the initial variable. So we'll get into the mechanics of how this works on the back end, but the concept is that you basically want to figure out what the type is of the first variable first, and then apply that type to the rest of them. So we're going to need to support calling multiple variable declarations, and of course we're going to use recursion to be able to solve the parsing of multiple variable declarations. So you can see that I pretty much, every time we call the function, I increment the recursion. That way we know how deep we are in terms of parsing a variable declaration. So once you increment this, I change this code here. Basically, you want to check to see if recursion is equal to 1. So if you are at the first point of processing this variable declaration, you want to do this special setup. So you guys know, as per usual, we do the same thing in every single function. We process our access types, so we add them and then we free up our access types. Then we check to see if we have a storage type. So this goes back to that thread local that I was talking about earlier. So if we have the thread local pre-appended before the name of our variable, then of course we want to add that, because on the backend side, we want to know whether or not this variable is a thread local. So we add this current token, or we add the thread local token to the current branch. And otherwise, if it's not a storage type, then we want to decrement the current token. Because if you remember, The only way we figure out whether it's a variable declaration, we have to be processing the current token at hand and then looking forward to see if it has the correct format. So we want to just go one character behind, and let's say if we were processing size, we would want to go here, so that way we can consume this identifier. So once we do that, we expect or we consume the name of the actual variable, and I have some test code here. Don't need that. Um, Also, you want to do this as well. So I'm going to do this again and say recursion is equal to 1. So basically, if recursion is equal to 1, you want to try to figure out how you're going to process the type of the first variable. So if recursion is equal to 1, then basically you want to see, all right, well, if we have this, where we have just a single colon, you want to expect that colon and parse a utype, because the expectation is immediately following this, basically telling the compiler, I want to explicitly declare the type of this variable. So of course we parse the utype, which is going to represent that, and then we check the next character after we parse our utype. So once we parse this, then we want to see if we have an equals, and if we do, then we can of course parse a expression here to get the default value of our variable, and that way we can initialize our variable. Once we do that, of course, we're going to advance and we want to parse an expression. Now, we don't really need to add the equals token. We just need to parse the expression, so that's why I didn't add it to the branch. Otherwise, if we have the other scenario where we do not explicitly provide the type of the variable, we basically infer the type, then we want to immediately process an expression following that. So in this case, we want to explicitly add the token to denote that we are in fact inferring it, because on the back end, we're going to need to know that. That's very important, because if you think about it, we're parsing an expression on both situations. We're parsing it when we explicitly declare the type and when we're inferring the type. So we need to check to see if we have this token, then we immediately parse the expression and derive the type from there. Once you do that, then basically once recursion is past 1, so once you've called back into this multiple times because you have, subsequent variables attached to the same one, then what you want to do is you basically want to only allow equals, right? Because when you think about it in terms of a compiler perspective, it doesn't make sense that you have, this size variable, and let's say it's of type int, and maybe you give it a default value of 1000. And it doesn't make sense for you to infer the type of A and say, the default value of this is 100, because you already know what the type of A is. From the compiler's perspective, the A variable is kind of attached to this size variable in terms of the type. So you don't really need to infer it. That's kind of weird. So I basically only allow the user to type in equals here to denote I want to assign it a default value. So, we just pretty much do that. We advance one, and then we parse an expression. So it's pretty simple on that side if you have multiple variables. Now let's kind of see how we do the actual processing of multiple variables. So how do we actually process this portion of code? So if we look here, we can see, all right, so after we've pretty much figured out how to process the initial type of our variable, and if we don't have the type, then we want to infer the type, we process the expression, we want to check to see if we have a comma. If we find a comma, that means we have other variables that are going to be attached to this one that we can derive the type from. So we, of course, expect the comma here, and then we dynamically call back into parse variable declaration recursively. And this is very important. So if recursion is less than or equal to 1, we basically want to pass in branch. Otherwise, we want to pass in AST. Now, the reason why you want to do this is because on the back end, and here I'm actually going to show you guys this as well. So I'm going to do compile, and I'm going to go to post process and resolve all fields and resolve field. So the reason why you want to do this is when we get to the back end side of our compiler and we're actually trying to figure out, and you guys don't really need to know what this does right now, but when we're trying to figure out the types of our variables, we're going to, of course, get the first field, and then we're going to pretty much try to figure out what the type is of that variable. But after that, we're going to need to have a list of all of the other variables. Now, if we just passed in branch, then it's going to format this in a very nasty way. So we want to basically flatline it to where every single variable AST is attached to the AST of size. And we'll see how that looks in a little bit, but you can kind of get a gist of how it's going to look here. So the variable AST of the first variable has all of its sub AST. So it has, its expression, so we can infer the value. It has its utype, so that way we can figure out the type of the variable, but we also want to flatline it and add the variable declaration ASTs to the same AST. So all we have to do on the back end is just do a simple for loop. So that's kind of why I decided to do that. It makes it a lot easier for processing. That way I don't have to recursively call the same function over and over again. So again, once we do that, so once we've recursively called to parse a variable declaration, if recursion is 1, then we want to expect a semicolon. So basically what that does is if we parse this, right? So let's kind of go here. So if I have like a symbol A, here's how the flow of this logic is going to go. So we start processing size, recursion is going to be equal to 1. We process A, recursion is now 2. Once we're done parsing A, recursion is going to decrement and it's going to be equal to 1 again. And after we finish parsing our second field recursively, and once it gets decremented down here, we're going to want to check this, and that's going to allow us to be able to process this immediately afterwards. All right, so in the case where we don't have a comma, this represents variables that don't have excess variables attached to them, and it's just like a single variable. Then what we're going to do is we're going to want to parse the getter and setter. So we're going to check to see if recursion is equal to 1. And if so, then we want to immediately expect a semicolon because we have semicolons at the end of every statement in our programming language. And then immediately after that, we want to parse our getter and setter. So getters and setters have a specific formatting. So set has this formatting, value, and we have that. Whoops. All right, so here's the formatting for set, and here's the formatting for get. You don't really need to know much more about how the getters and setters work. We'll go over that later on. But pretty much what you need to do is check for the next character to be either get or set. And this is very important because basically when I'm processing this, you don't want to force the user to have it in a specific formatting. Meaning, you don't want the user to have to put the getter first and then the setter second. You want the user to be able to do whatever they want. They can put the setter first and the getter second, or the getter first and the setter second, or they could have just a getter, or they could have just a setter. We want to leave it completely up to the user to format it how they want, so that way it's not annoying. So in order to achieve that, we are going to want to, if we pick the next character and it's equal to get or set, then we want to check to see if it starts with get. If so, we want to try to parse a getter, and then we want to try to parse a setter. Otherwise, we want to try to parse a setter first, and then we want to parse a getter. So doing it this way allows us to not be constrained to which one comes first, or whether or not we need both of them at the same time. So let's kind of see how this code looks. So if we go here, parse getter, it's very simple, guys. Getters and setters are very simple ASTs. So all you need is you need to check the next character to see if it equals to get. And even though we've already checked it at the previous level, you need to check it again when you call the function because this allows you to format in either way, as I mentioned before. So you want to check the next character. If it's equal to get, then you want to create a branch called AST getter. You want to expect that token. You don't really need to add it here. I can probably just set that to false, but it's totally fine. You can add the token if you want. We're not going to use it on the back end though. Immediately after that, you want to parse a block, and that's pretty much it. So I actually screwed up the formatting here. So here's how getters look. So here's the actual formatting for getter, and then here's the format for setter. So let's see how setters look. So if we look at a setter, when we parse our setter here, we of course check to see if the next token is equal to set. If so, we create a branch called AST setter, expect that token. We expect an identifier. This is important because the way that getters and setters are going to work, the concept of how getters and setters are going to operate in the language is this is basically going to be a function call. So a getter is effectively going to create inside of the class a define get underscore field name, right? So whatever the name of your field is, and it's going to return the type of the field. So in this case, we would create a function called get underscore size, and that will return an int, and that's how that will work. So you can put, whatever code you want in here, and then once you're done putting that code in, you can return some value. But in setter, it's a little bit different. So when we have a setter, the philosophy behind that is we're going to need to create a separate function called set underscore field name, and we're going to need to pass in the type of the field. So we're going to need to say number of type int, and we're going to return void, so nil, and the return value of this is merely a design decision. You guys can do whatever you want. I will briefly probably explain on how you can return a custom value here when we get to it, but for me, I decided to just return nil. But yeah, so to replace this here, I'm going to do the size. So setters would basically create this function. So this is why we kind of need this value here, because basically this value name or this variable is going to represent this here. So that's kind of how it's going to be formatted. So let's go back, and yeah, so of course once you parse your identifier, you need to expect the pointer symbol, and then you parse a block. So that looks to be the correct formatting here. You don't really need this pointer here. You could probably just do that. The reason why I added the pointer is because this just looks weird, right? Like it's just like you have your set and your value, and it's just kind of sitting or floating. So if you guys want, you can probably do like set, and then you can like put parentheses around it and expect like a left paren, a right paren, and then expect an identifier in the middle. But in my case, for my formatting, I decided to use this arrow just to kind of break things up. Once we do that, that's pretty much it. So let's go back to parse variable declaration. So after you pretty much do that, once you parse your getter and setter, the final thing you want to do is decrement recursion. So that way when you exit this function, your recursion gets incremented and decremented. And that's pretty much it, guys. There's not much to it. And before I show you guys the formatting for how this is going to look once we generate this AST, I want to kind of do a recap on pretty much everything we've learned in the parser thus far. Also, just to kind of make sure you guys are in line with how the language is going to be parsed and everything like that. So I'm going to go here to parse, which is our top level function. So we've gone over a lot of things so far in this YouTube series, and pretty much at this point, the last thing that we're going to probably do is we're going to need to create the function parse expression. And once we're done with that, I mean, we're finished. We can basically start working on the backend side of our compiler. Our parser is not that complicated. It does take a lot of explaining, however, just to kind of get you guys up to speed and kind of understand what's going on. But yeah, so we've gone over pretty much, let's kind of see here. So we've gone over how to parse a module declaration. So here's all of the, basically all the ASTs you're going to need to have at the top level. You're going to need to be able to process a module declaration, an import declaration, a class declaration, mutate, method declaration, alias, interface, enum declaration. Oh, I guess we haven't gone over enums, so that'll probably be the next episode before we get to parsing expressions. So I take that back, but you're going to want to parse enum declarations, variable declarations, and you want to make sure you add all of these ASTs to your parse all function. And of course, obviously, like you don't want to at the top level, you don't want to support parsing operator overloads because operator overloads wouldn't work in this context. This is basically going to be considered the static global scope, and pretty much any function created at this level is going to be created as a public static function by default because it's created at the top level and it's not bound to an instance or a class. So just keep that in mind. Certain things that we would process at this level wouldn't make any sense. So let's kind of go into parse class declaration to see what we also should be parsing there. So in your class declaration, you want to be able to parse module declarations, of course, class declarations, mutate, interface. Of course, you want to support your getters and setters, so you want to add this code here as well. And I have this in a couple spots. So you want to check to see if the current token is equal to get, and you want to check your access types because, I mean, you can't really have access types on getters and setters. Um, and then you want to basically complain about it. In my language, getters and setters are only allowed legally immediately following a variable declaration because you need something to attach this to. So you need to attach this getter and setter AST to a AST that is a variable declaration. Otherwise, we wouldn't know what these getters and setter ASTs are referencing. So you want to basically say unexpected get declaration. You want to decrement the current token and of course parse your getter. Because when you come into here, we're going to need to peek forward one. So you're going to want to decrement your current token. For setter, it's pretty much the same story. You're going to want to check to see if the current token is set. And if so, then you want to make sure you don't have any access declarations. If so, you want to complain with this error here for illegal access declaration. And then you also want to complain about not expecting a set declaration. After that, of course, you want to decrement your current token and parse the setter. But yeah, so in terms of other ASTs, you want to be able to parse import declarations, variable declarations, alias, enum, init, method declarations, constructors, and of course your run-of-the-mill bracket and end-of-file logic down below. Now, as you guys notice, I didn't allow the user to parse init declarations at the high-level scope of parse because it doesn't make sense to have this AST here. So in this instance, the parse init declaration would be created inside of the parse all function. And I would just basically add that to the list of ASTs that I would check for. So this is another example of other code that would not be put at the highest level. So once you have all of that added to parse class declaration, let's kind of see what I support for parsing interfaces. So for interfaces, you want to have module declarations, interface declarations, mutate, import, your getters and setters, alias, variable declarations, method declarations, init, constructor, and your run-of-the-mill other code that goes down here. So pretty much for interfaces, the only thing I'm going to support in terms of my language is you can see here there's like tons of errors. You're going to want to, for every single AST that is not in fact either a interface declaration or an alias declaration or a method declaration, you pretty much want everything to be complained about because interface declarations will only allow for us to create delegate methods because interfaces aren't classes. They don't have the same functionality of classes. They're much more limited in terms of what you can do. So just make sure that you put your errors here and just say unexpected, whatever the declaration is. So unexpected mutate declaration, unexpected module declaration, unexpected imports, so on and so forth. So you guys get the idea. Also, another thing to note for method declarations, when you guys are processing this, now this only applies for interface declarations. As you guys know, here's kind of how I parse method declarations, right? So I don't even think I went over this in the previous episode, but basically in order to, once I have decided that what we're processing is in fact a method declaration, the way I figure out whether to call operator declaration or method declaration which function is I check to see if the next token is equal to operator. If so, then I parse that declaration immediately. Otherwise, I parse method declaration. But what you don't see here and what's different here is number one, of course, operator declarations are not allowed. And then when we process our method declaration, I check to see if the branch last AST is equal to a delegate declaration. And the reason why you want to do that is if you guys remember, when we're processing a function, this is considered a AST, well, this is actually an operator declaration. But like if I define a foo function here, this will be considered pretty much a AST method declaration, but once I remove those curly braces and I put a semicolon here, this is now considered a delegate function. So we just want to make sure that pretty much once we add the method declaration to our branch, and of course it's going to be the last AST because that's how it works. We want to get the last AST and just check that, and if it's not a delegate, then we want to say unexpected method declaration. Because for interfaces, we don't allow for the user to actually write the implementation of the function. So that's just one little small caveat. If I go and do a search for parse method declaration and I go to parsing a class block, you can see here the code is a lot more tame, right? So this is in the parse class block function. I check to see if the next token is an operator. If so, parse the operator declaration, otherwise parse method. So I don't have like all of this extra code here where I'm complaining about operator declaration and I have this like branch check. So just keep that in mind. But yeah, so that's pretty much it in terms of everything that you're going to need to have in all of your functions. So definitely I would recommend if you guys have been following along, you should be fine, but just give this parser.c++ file a review just to see if maybe you missed some code or maybe I overlooked something. I think for the most part, I've pretty much reviewed everything in this code base, with the exception of course, parsing expressions. But I think for the most part, we're good. But just to be sure, I would definitely recommend checking this file out. That's going to be located in my lib grammar front end parser, parser.c++. So that's where you'd be able to locate it in my project. But yeah, so let's now kind of see how variable declarations are going to be looked once we generate them. So I'm going to go back up to the parse class block and I'm going to copy this code, go down to parse variable declaration and paste this at the very bottom. So I'm going to do a bunch of different variable formatting so that way we can kind of see everything all at once. So we're going to have a regular variable with an explicit type. We're going to have a default value. It's going to have a getter and setter. And here, let me remove this code. So it's going to have a getter and it's going to have a setter. And then we're also going to have another variable declaration. And here I'll make this a lot simpler, otherwise it will be very large, where we basically infer the type of the actual variable. And then finally, let's create a foo variable. I know, great name, right? We're going to have a foo of type int and A, B, C. So we'll have one where we have multiple variables. So let's kind of remove any noise here and let's see what our compiler outputs. All right, so I've pressed continue about 3 times because we have roughly 3 variables here. So we can kind of see pretty much all of them all at once. So let's scroll up here and take a look at all of our variables. So we're going to have the first variable that we're going to check out, which is size. So we're going to have size, and we're going to have this token denoting that we explicitly are requiring the type of this variable. So we're going to have 4 ASTs here, which is quite a lot. We're going to have first our utype AST, and that's going to represent the type, of course, of our variable. So this is pretty straightforward. We just have the type explicitly defined here. After that, we're going to have our default value of the variable, or the initial value that it's being initialized to, which is a AST expression of a literal of 1000. After that, we're going to have 2 ASTs. So we're going to have our getter and we're going to have our setter. Our getter is going to have the token here, and it's going to just have an AST block. Our setter AST is going to have set the name of our variable and our pointer. Like I said, you probably don't even need to add that. That's kind of unnecessary. And then finally, we have our block. So any code that's going to be in AST block are going to be a list of statements that we would process. And after that, we have our test variable here. So let's scroll down. So this is the case where we infer the type of the variable, and this is kind of how it looks. So we have our AST variable declaration, test, the infer symbol, and we just have one AST with an expression. So it's pretty straightforward. Then of course we have a literal expression of 9. So as you can see here, in order to figure out the type of test, we're basically going to be forced to process this expression. And then finally, we have our variables. So as you can see, we just have our first variable called variable C. So because this is recursive, I'm going to have to call this 1, 2, 3, 4 times. So I'm going to go back to here, go to our debugger, 1, 2, 3. Okay, so I guess I had to do it 3 times. So now we can look at our foo variable. And here's a perfect example where we can kind of see why we need this recursion variable for adding either branch or AST, so that way everything is kind of in line, so that way it's easy to process. So when we're processing our foo variable, we're going to have our utype as our explicit declaration, or we could have, of course, a infer type with an expression and the infer symbol. But in this case, we just have our explicit type declaration here. So after our utype, we have basically our variables. So here's why I wanted to add this, because basically you can just do a for loop on all of these ASTs and process whatever you need to process. And yeah, so you can see here we have variable A, B, and C. So yeah, that's pretty much it for today. Like I said, we're probably going to be looking at how to parse enum declarations next episode, and then we can kind of get into parsing expressions. So hopefully that made sense. As usual, if you guys have any questions, definitely write them in the comment section below, and I'll try to get to them as quickly as I can. And of course, as per usual, if you guys would love to help support the channel, definitely head over to my GitHub repository. You can get there by going to github.com/androdevcd/sharp. And when you guys get over there, definitely watch, star, and fork the repository. This is going to give the language a ton of more visibility and lets other developers know that the language exists. Also, if you guys are curious about anything going on with the language in the day-to-day as I'm kind of developing it, I would definitely recommend heading over to the remastered branch. This is the most active, up-to-date branch where I do all of my work on, and I usually update it on a daily to weekly basis. And you can see that by heading over to my commits. I usually put some pretty wordy commits here, so you can kind of get a gist of everything that I've done in the commit itself without having to really look at much code. Also, quick side note, I managed to make objects a lot smaller. So now, because I'm pushing for supporting 32-bit operating systems, the size of my objects are now 32 bytes. So they've gone all the way from being about 72 bytes per object to now being 32 bytes per object. Now, that's still pretty big, especially considering Java standards. I think the size of a single Java object is like 16 bytes or something like that. So it's not perfect, it's not the smallest, but going from 72 bytes per object to 32, I think is a pretty good feat. So also, if you guys are curious about maybe learning things that I've done in the past to the language, or maybe you're curious about stuff that I'm looking to add into the future, I would definitely head over to the doc folder. I usually update this one pretty frequently. And if you're looking to find out maybe things that I've added to the language in the past, you can check out the changelist file. That's going to be pretty much every major update that I've had in the language thus far. And it gives a detailed description of all of the features and bug fixes that I've added to each of those versions. And if you're curious about stuff that I'm looking to add in the future, I would definitely recommend checking out the roadmap file. Like I said, this one is pretty much updated all the time. Like I rarely update this file, but this one gets updated often because not only does it hold everything that I'm looking to add to the language, it also holds all of the things that I've done to the language thus far as well. So you can kind of check out that one. I think this file is pretty interesting to look at. So that's going to be it for today, guys. Hope you enjoyed the video. Definitely like, comment, and subscribe if you guys like what you saw and you want to see more. And until next time, I'll see you guys later.